What up, everybody? This is Tom on Hubbard Waves 2 Minutes, and in this video I'm going to react to a video that was sent in to me. I believe I'll be able to provide some commentary. It should be a fun video, and hopefully we'll find many things for me to correct or provide insight, or like I said, get some commentary on. So the video is a YouTube short. So I'm going to go ahead and play the video in its entirety, and then we'll go back through it, and I'll just start providing some insights on what is probably accurate or inaccurate about the video. All right, so let's go ahead and get to it.
This the hydrogen bottle from China, just throwing that out there, and then we have our medical grade water from our Kangen machine. Let's see how much hydrogen is in this. Okay, so obviously there's none in Dasani bottled water. This we have a negative, so there is hydrogen, it's just a very low amount. And then we have, wow, almost negative 800, so it just shows how much more hydrogen comes from our water. Now he's testing it with pH drops, which measures potential hydrogen. And as he blows the CO2 into it, it shows that it doesn't hold the charge. It goes, there you go, it's gone. It doesn't hold. And then check this out. Yep, there's the machine. Yep, doesn't change.
All right, man. So it's a lot going on in this video. And so let's take it bit by bit and try to go ahead and debunk a lot of information, or let's debunk what's happening in the video itself. All right, so I'm gonna play it, and then I'll stop it and I'll start to talk about some things.
This the hydrogen bottle from China, just throwing that out there.
All right, so this is a little demonstration that they're doing. He does pour this water from this hydrogen water bottle. There are basically two versions of this particular bottle on the market. There is a PM version that supplies pure hydrogen gas that can dissolve into water, and then there is a very cheap version that is AWI technology, alkaline water ionizer technology, and basically essentially both electrodes, the cathode and electrode, are exposed to the drinking water. Therefore, you're going to be producing hydrogen gas and oxygen, ozone, and other things that can be produced, chlorine, all this kind of stuff can be produced. We've tested this bottle before. It's a bottle no one should ever drink. It's not a high quality bottle. She provides a little basically statement that, it's from China. And we need to be mindful that majority of hydrogen water bottles and hydrogen water products are manufactured in China. And just because it's made in China doesn't mean it's poor quality. There are beneficial and reputable manufacturers in China, and bad ones in China. There's manufacturers that are reputable in Taiwan, and not so good ones. And then there's same thing for Korea, and same thing for Japan. So I've been in this industry a long time. Just because it comes from one particular country does not mean it's inherently always going to be good. And so you cannot just say because it comes from China it's bad. That's not true. So that being said, we can go ahead and keep going.
And then we have our medical grade water from our Kangen machine.
All right, medical grade hydrogen rich water. So medical grade, that is a funny term to use for the water produced from a Kangen water system. A Kangen water system, if you don't know what that is an alkaline ionized water device, and it's sold by the company Ionized. And that system was classified as a conventional water ionizer. So they basically run the water, your drinking water, through a filtration process, a basic filtration process, by the way, and run the process of water electrolysis using their particular hydrogen cells, and it will produce a form of hydrogen-rich water that has a alkaline pH and varying levels of dissolved hydrogen gas depending on the source water conditions. Therefore, That's what it is. Now, calling it medical grade is funny because that would be similar to the degree of calling, let's say, dental floss, a medical grade product. Dental floss, if you don't know this, is a class 1 medical product. But we all know that classification does not mean that it has the same merit as, let's say, a ventilator that goes into a hospital, or something along those lines. Like, we clearly know the distinction. This is what's going on with water ionizers. Virtually all water ionizers coming out of Korea and coming out of Japan are going to have this medical certification. So it is true that it can be classified as a medical device. But this classification is primarily due to some early research that was happening in the 60s and 70s. And when they noticed that basically there was some improvements for gastrointestinal discomfort with like ionized water. And there was a basic regulations and certifications that needed to happen for these water ionizer companies. So nearly all of them have this certification. It doesn't make, a NAGIC special or something or unique. So this was done by the Japanese Ministry of Health, Labor, and Welfare, which is equivalent to our FDA, and even also the Korean FDA. They have similar certifications that need to be had if you're going to sell a water ionizer. Like I said, the same thing is for dental floss. You can sell dental floss here in the United States, and it's going to be the same kind of certifications that need to be that happen for dental floss because it's a class 1 medical product. Does not mean it has the same degree as some product that's going to product or like medical device is going to be used in hospitals. That's not what this is talking about. And so, no, I would not call it a medical grade hydrogen rich water. All hydrogen rich water, if it has therapeutic levels of hydrogen gas dissolved into it in purified water, can be therapeutic, predicated on the research. But some product that has some certification that is necessary from its regulatory bodies in their country does not make it inherently better than any other form of hydrogen rich water. And in most cases, I would say in virtually all cases, hydrogen rich water that's used in the studies is not using water ionizers. All right, let's keep going.
Let's see how much hydrogen is in this. Okay, so obviously there's none in Dasani bottled water.
Okay, first things first, they're using an ORP meter. Big no. You definitely should not use an ORP meter to try to investigate the therapeutic potential of hydrogen-rich water. The reason for this is hydrogen-rich water ORP meters can basically detect the presence of hydrogen gas or a reducing agent in the water. It cannot accurately tell you how much hydrogen gas is in that water or what reducing agent is in the water. There are negative or harmful reducing agents. So just because the meter goes negative does not mean the water is actually beneficial. You can actually produce a negative ORP with something like aluminum, and we all know that aluminum can be toxic and damaging to our bodies at certain obviously levels and things like that. So no. Also, for those who don't know what ORP stands for, it stands for oxidation reduction potential. It pretty much, so you understand what ORP is in a nutshell. ORP basically is based on the Nurse equation from Walter Nurse. He was a German chemist, and in the late 1800s, early 1900s, basically. And based on the Nurse equation, it allows us to read what's called redox couplets in solutions. And so redox couplet would be like the reductive state and the oxidative state of a chemical species. So let's take, for example, chlorine. Chlorine is a gas, so it'll be Cl2, right? That's a chemical formula for chlorine. That's its oxidative state. Its reductive state is called chloride, Cl minus, right? So this is what ORP meters can pick up on, the actual redox couplets and their, let's say, their relative concentrations within water, and then it basically converts this into a millivolt or into a voltage potential, so you can read this, right? You can go ahead and essentially be able to understand if the water is more reductive in its characteristics or if it's more oxidative in its characteristics, and it's going to take away it's going to take away electrons, or it's going to accept electrons, right? So that's what this is all going on. ORP meters are definitely not a useful tool for hydrogen-rich water, because the redox couplet for ORP meters when it comes to hydrogen-rich water is H2. That's going to be the reductive state. And the oxidative state is going to be H+. H+ is hydrogen ions or hydrogen cations, or we know them as protons, which dictate pH. So there's far more protons in water than it will be hydrogen in water. So what's going to influence the ORP far more, what's going to influence the ORP more? The protons that are in the water or the H2? And it's going to be the protons. So in other words, the pH is going to highly influence a ORP reading. It's pretty wild. So what we can say is that H2 dissolved into water is definitely what's going to cause the ORP meter to go negative. But the pH is going to have far more of an influence on what the actual ORP reading will be. And the more the more alkaline the pH, the more negative the reading will be. And you can literally have 100,000th of a milligram of hydrogen gas dissolved into water, and it will make the meter go negative. So you don't need an awful lot of hydrogen gas for it to go, negative. And no one's going to sit here and say, based on what we know in the research, that 100,000th of a milligram of hydrogen gas dissolved into the water is actually going to be beneficial for you. So there's some issues with ORP meters when it comes to hydrogen-rich water. And for that matter, most waters, when you're talking about the things that people want to try to understand, what is actually in the water, how much of it's in the water, all these kind of things, it will not tell you that. That's not what it can be used for. So they're already failing by using an ORP meter and showing their hand that they're uninformed, unfortunately, and they probably should do a little more studying before they start doing demonstrations.
This, we have a negative, so there is hydrogen, it's just a very low amount. And then we have, almost negative 800.
Okay, so now you saw that basically the bottled water had a positive ORP, and the H2 bottle, hydrogen water bottle, had a negative ORP, but it was a, slightly negative ORP. And this could be for a host of reasons. We actually don't know. For example, we don't know what type of hydrogen water bottle he's using. It could be that it's because it is one of those versions of the hydrogen water bottles that are cheap and use old technology, and is producing not only a reducing agent or an antioxidant like H2, but it's also could be producing oxygen and other actual oxidative chemical species. So we have no idea. But what we do know also is that as the video continues, like we saw this, that water is kind of towards neutral. So meaning, the proton concentration of the water is going to be different than if it was more alkaline or any of this kind of thing. So obviously, if the water is more acidic, then it's going to tend to read more positive. If the water is more alkaline, it's going to tend to read more negative. And this is just why ORP meters have their limitations, why you shouldn't use them. They're highly influenced by, like I said, pH of the water, highly influenced by minerals. They even temperature can affect it. So you just need to be mindful that there's going to be gaps. And then you obviously saw that the Kangen water, or the ionized water, was really negative 800, which, by the way, everybody, so you know this up front, I actually own a Kangen system. I had one from over a decade ago. Used to do demonstrations like this, learn accurate information about why these things was wrong. You should never use these kind of demonstrations to help people understand it, because you otherwise mislead people. And that negative 800 was likely produced by basically running the water on its strong water setting, which uses the highest applied voltage, which typically uses an electrolyte solution, which increases the conductivity of the water at the plates. and basically produces somewhat of an elevated sodium hydroxide, like a mild lye solution. It's really, really high in the hydroxide, which is alkaline component of water, and adds salt to it. And so therefore, that water is going to be really high in its pH, and they tend to slow the flow down. So it even gives more contact time for the water going over the plates to basically end up producing a high pH water, something over 11 pH. Now remember, pH is a logarithmic function. You're going up in tens. So you have a big gap of proton concentrations from 7 pH to 11 pH. And so that's why that ORP meter reading, or RP reading, was negative 800, was likely due to the pH of that water is really high. And it could be something like 11 or 12 pH. And he likely prepped that water before doing the demonstration, knowing that it's going to have a really, really high pH, slow the flow down on the system to where the water is basically dribbling out, and then putting that into the bottle, and then doing the demo. And so the pH can be really high to make that ORP reading look exceptionally well.
So it just shows how much more hydrogen comes from our water. Now he's testing it with pH drops, which measures potential hydrogen.
Yeah, so how much more hydrogen is going to come from the water? No, actually, water ionizers are pretty much notorious for having relatively low dissolved hydrogen concentrations in water, because they were designed to produce a alkaline pH in the water. They weren't optimized or designed to produce dissolved hydrogen gas within the water. And she's conflating basically, you see on the screen talking about active hydrogen and molecular hydrogen, which active hydrogen is a misnomer, and actually was tied to a mistranslation from early Japanese studies to English. And so active hydrogen really doesn't actually make sense when you're talking about molecular hydrogen, which is biologically inert, doesn't readily react with anything, it's quite stable. It's not very active in that sense. It's not reactive. And so that's what it should have been probably translated to as reactive hydrogen. And that is more related to hydrogen atoms. Hydrogen atoms are a free radical. They're one proton, one electron. They're very reactive, and they are in a lot of different compounds, definitely seen in organic chemistry. They are reactive, and they exist in many different compounds. So this is what it's likely talking about with active hydrogen. Yeah, so we already got issues there. And then she's talking about more hydrogen gas, or more hydrogen being in the alkaline water, which is funny because if you are talking about, you have to distinguish between which forms of hydrogen you're talking about. If you're talking about hydrogen cations or protons, then it actually has less hydrogen in it, because that's why the pH is so high. If it had more hydrogen, the pH would be more acidic. If you're talking about hydrogen cations or protons, if you're talking about molecular hydrogen gas, 2 protons, 2 electrons, which is the gas that's dissolved into the water, yeah, water ionizers tend to make, let's say, for example, the ST501 from the company Ionized, based on our testing over a decade, they tend to make brand new out of the box, with good source water with good source water conditions and conductivity of the water itself, good mineral ions in the water. You're going to end up making something around 0.5 ppm or milligrams per liter up to about 1 milligram per liter, or ppm. A K8 system, which is like the highest version of the Ionized water ionizers devices, they're going to be making something fresh off the box, depending on your really good source water, 0.8 ppm on average to about 1.2 ppm of hydrogen gas dissolved in the water, these are in today's industry and market relatively low concentrations, and it's really hard to get above that. Most of these systems, the ST501 and the K8, they tend to dissolve only about 20% of the hydrogen gas that they actually generate per minute. So Yeah, so they don't have any kind of dissolver technology to help hydrogen gas dissolve in the water, which is not very water soluble. Hydrogen gas has low water solubility, so tin dissolver technology helps. Whether that's like creating smaller nanobubbles of hydrogen, or whether that is using things what do you call it? Partial pressure or PSI to help hydrogen gas dissolve into the water. There's things that you can use as dissolver technology. It doesn't have any of that. It just uses water turbulence through the cell, water traveling through the cell, ripping off nanobubbles of hydrogen gas and dissolving that into the water. So there is no dissolver mechanisms for the system. So they're going to be limited in how much hydrogen gas they can dissolve based on the available gas that they're generating. And if they were to generate or dissolve something like 40% of the gas or even 50% of the gas, they would essentially basically saturate the water at 1.57 or 1.6 milligrams per liter ppm as a maximum, but they don't do that. And that is a limitation for the technology itself. Let's go ahead and continue and see what else is there to actually cover.
And as he blows the CO2 into it, it shows that it doesn't hold the charge.
Yeah, so he's blowing CO2 into the hydrogen water bottle, and that it's not something that's unknown about why the water would actually become more acidic. CO2, when you dissolve it into water, basically reacts with water and becomes carbonic acid, and this is a rather weak acid, but it'll actually be something that causes the water to become acidic because water is not a buffer. Water has no buffering capacity to it. Typically, buffers is going to relate to the alkalinity of water, meaning how well that water or like how many buffers are in that water. So think of something like mineral carbonates, sodium bicarbonate, right? This is a buffering agent, meaning, for example, like baking soda. Baking soda exists at an 8.1 pH. And the interesting about buffers and the interesting thing about baking soda is that if you were to add a alkaline agent to baking soda, it's going to release acid to try to fight and maintain its 8.1 pH. But also, if you were to add an acid to baking soda, it's going to release a base. It's going to release hydroxide to try to fight to maintain its pH. So it's going to buffer, right? It's going to have buffering capacity to fight and resist to maintain its pH. Water doesn't have that. And it's really important that the water doesn't have that because our bodies are going to move that water and alter the pH of that water, predicated on organs, tissues, and basic physiology of the body. That's what's going to do. So that water, no matter what pH it is, it might not survive your stomach, which produces which produces hydrochloric acid. It's far stronger than say carbonic acid. And then if it's not altered by your stomach, it's going to be altered by your intestines, like your duodenum or your small intestines. If it's not altered by then it's going to be definitely altered when it hits your blood, which is about 7.365, 7.45 pH. And it's tightly regulated to maintain that pH through a buffering system using bicarbonate, or I should say, using bicarbonate, and also your lungs and your kidneys. But anyway, it's going to maintain that pH. If you go higher, you get alkalosis. You go lower than that, you get acidosis, and both of them can be problematic. So, So either way, it's silly. It's a silly example to show that you can blow CO2 into the water and change it. And all he's doing is, if there was any hydrogen gas that was in that water at therapeutic levels, he is sparging. The principle is called sparging. He is sparging out the hydrogen gas. Hydrogen gas just got dissolved into the water, filled up the little nano cavities between the water molecules that are held together by hydrogen electrostatic bonds. So they're going to form these little pockets that hydrogen gas can dissolve into. When he's blowing into that cup into the water, he's going to sparge and force out the hydrogen gas to come out of solution. So all he did was just basically reduce the therapeutic potential of that water if it was therapeutic to begin with.
And as he blows his CO2 into it, it shows that it doesn't hold the charge. It goes, there you go, it's gone.
She said it doesn't hold the charge, by the way, as well. And by the way, water doesn't technically hold a charge due to the principle of electroneutrality, meaning that, basically negative ions or ions in water must balance each other out. So hydrogen water has a net neutral charge. So this is one of the misconceptions from ORP meters, because you read a negative or positive voltage potential using the ORP meter. Therefore, you think water somehow holds this negative or positive charge, like the meter is actually suggesting. And that's not true. You can look this up if you want to, but pretty much, due to the principle of electroneutrality, it's not holding a charge. So that's another blunder by the video itself, unfortunately.
It doesn't hold. And then check this out. There's the machine.
So they show the K8 system, and then they show him blowing into the Kangen water, or the hydrogen-rich water produced from the system, the alkaline hydrogen-rich water produced in the system. And the reason why it's basically taking so long to change is because it has more hydroxide to deal with. Like I said, the pH of that water is really high. So eventually, if he kept blowing into it over a course of a few minutes, it probably will start. You'll see it go from purple to blue to green, neutral pH, right? This kind of thing, slightly alkaline in the blue. But the likelihood, what's most plausible, is that he ran that water on he ran that unit on its strongest setting to produce a really high pH water, and it's just taking longer for it to be lowered by his carbon dioxide that he's breathing out.
Doesn't change.
Yeah, so what you're seeing here is basically that, like I said, the other waters don't have any buffering capacity, and due to the high hydroxide concentration or alkaline component of water, which is hydroxide OH minus concentration of the alkaline water that he had, all he did is just move that over to the other glass, and there's no buffering capacity, because the likelihood is that he took the same bottled water that he has over here, Dasani, which is RO water pretty much. It has no mineral compounds in it. And, things like, calcium carbonate, right? Like things like these are buffers that can be, buffering minerals that can be present in water in low levels. Dasani doesn't have anything. It's purified water. It's RO water, basically. It's removed from its minerals. So there is no buffering capacity to this water. Water is not a buffer in it. Even if it had any kind of buffers that could be in minerals that could even been in the water, they're removed. So it's easily altered and changed, and which is not a bad thing. He's showing that it's actually a good thing. Your body can change that really simply and easy without having to neutralize the acid or anything like that. So, but he also is showing that this is about to make the water go really negative. And that's to be expected. He just dumped in a ton of hydroxide and increased the pH of the water. And like I said, 100,000th of a milligram is all of HU. That's all that's needed to make the meter go negative. So now you just drew the pH really high, and with a pretty low HU concentration, probably really low HU concentration, all it did was just make it go really negative because the pH is so high. So he's not showing anything that's spectacular or anything. So yeah, so that's it, man. That's what I saw. There's a lot more I could probably speak on. I could probably do an hour breakdown on this video. Unfortunately, I'm not going to do that. This is already pretty long-winded anyway. There's just so much that's in this video that it's pretty crazy, because I know I didn't catch everything. There's other things I could I could say. So anyway, hope you guys enjoyed this video. This is why you should follow and watch H2 Minutes. We try to do our best to make sure that you're receiving the most accurate information that's predicated on experimental data and medical research, tied to basic basic biology or physiology, and so that's what we try to do here, and we do it all surrounding molecular hydrogen research for your body. So hope you guys enjoyed it. This is also some demonstration like this also has been done with other people online. I'll go ahead and link that, and I have videos that break all this stuff down. So I'll have videos to our water ionizer series, and we'll cover things from the limitations of water ionizers to the special waters that are produced from water ionizers. And I'll also drop our video into the description for our ORP meters and why they should not be used, or ORP why it should not be used for hydrogen-rich water. And go ahead and make sure you guys have those resources in the description of this video. Alrighty. Peace.